Okay, so we're going to talk about molar solubility. And molar solubility is a term that's used and calculated to compare how soluble something is. Its unit is S, and its moles. Its unit. Sorry, its symbol is S, and its units are moles per liter, molarity. All right, and the reason when you're comparing solubility, you cannot compare Ks p-values. You have to compare your molar solubilities. All right. And I'll illustrate this with a problem. All right. Now, I want to set up a little table. Uh, Formula and ions and my KSP. Since all KSP equilibrium expressions are basically the your cation and your anion, all right, all KSP values are those raised to some exponent. If my formula is xy, I'm going to have two ions, and my KSP is going to be equal to x, the concentration of x, times the concentration of y. All right? These two things are going to be the same because however much of x dissolves is going to be however much y dissolves. So S would be equal to the square root of my KSP value. All right? If I've got x, one of these two, I've got three ions, my S, my molar solubility, becomes the cube root of my KSP divided by 4. All right? If I've got 4 ions, it's the fourth radical. I'm not sure what you call that. The KSP, oh, that should be a lowercase, divided by 27. All right? Just to show you where that comes from. So let's say XY, it's going to have X plus 3, 3y negative. So my KSP would be equal to some change of x and then 3x cubed. Okay? And this would come from a rice table, all right? Or an ice table. So this becomes 27 x to the fourth is my KSP, and x is my solubility, molar solubility. So to solve this, and I know I said x and I said here x, s, so they're kind of interchangeable. But the typical unit that I've seen with molar solubility is S, a capital S. So I'm going to rewrite this as 27s to the fourth power. So then I'm divide both sides by 27 and take the fourth to the, okay, like that. Divide by 27, then take the radical 4 of that. All right. Okay, I just checked with the math teacher. This 4 is called a root. All right. Now, these will work with any different salts. All right. But when you're solving for molar solubility, so like example, AgCl or barium oxide. All right. I want to go back to this. So I need molar solubility because when I'm comparing solubility, I can't compare KSP values. I have to compare S values, molar solubility. All right. Let's do an example. All right. One of my salts is MgOH, magnesium hydroxide. Its KSP value is this. All right. Silver chloride, its KSP is this. And LaIO3 iodate is this. Here's LA. It's Los Angeles. I'm not sure. It's the lanthanide element. I've never seen it. It's kind of a rare thing. Kind of cool. All right. So this has got 3 ions. So my KSP is going to be equal to S 2S squared. All right. This is going to be equal to S squared. And this is going to be 27 S to the 4th. All right. So my KSP for magnesium hydroxide is going to be, or my S is going to be the cube root of my KSP divided by 4. All right. So I'm going to plug this in. The cube root of 1.8 times 10 to the 11th divided by 4. Now this is equals S. This equals my molar solubility of magnesium hydroxide. So I'm going to plug this into an equation, not to an equation, into a calculator. I need to get it. All right. I'm going to plug this in. I'm going to pause this while I do this. Okay, there's my answer. Okay. It's really kind of glary. Oh, there it is. 1.65 times 10 to the negative 4th. All right. Now that's a molarity. All right. And now I got to do this one. Well, for Ag, my KSP is Ag plus Cl negative. So my molar solubility would just be S, or they're going to be both equal to some concentration, S. So my molar solubility, which is S, is going to be the square root of my KSP. All right, my solubility product. So what's the square root of 1.8 times 10 to the negative 11th? I just caught a mistake. I noticed I had written the same solubility product when I was typing this into the calculator. This one should be e to the 10th. All right. So that's going to change it down here to taking the square root of e to the negative 10th. All right. So I get 1.34 times 10 to the negative 5th. That's my molar solubility. Okay, now this one is a much bigger smaller equilibrium constant. All right. But you'll notice it's got 4 anions. So my molar solubility might be different. Let's check it out. My KSP is La, I guess it'd be plus 3, iodate concentration raised to the third. All right. And so my KSP is going to be equal to S, whatever amount of this, and that's going to be 3S. So I'm going to get this when I multiply these together. So my S, I'll show you that. So 4S, not 4S, S to the fourth, and that's going to be 27. It's going to be KSP. All right, 27 S to the fourth. And then to solve for S, my molar solubility, I would divide my KSP by 27 and take the root fourth of it. All right, so that equals 7.5 times 10 to the negative 12th, getting that number from there, divided by 27, 4. Okay? Okay, I did it on the calculator. You'll notice I get 7.25 times 10 to the negative 4th. All right? Now, then, if I look at this, these three values, you'll notice that in terms of solubility, molar solubility, lanthanide is more soluble than the other two. Then comes magnesium hydroxide, followed by silver chloride. Even though silver chloride has got the largest KSP value. All right? And that's why we need to think about, that's why we need to use our molar solubility to compare how soluble something is to determine which more soluble, not the KSP values. All right, hope this has been helpful.